Hello and thank you for watching. In this video we're going to define the vector product. Okay, so to start off, the vector product is a function which takes two vectors in R3 and then also maps them onto a vector from R3. And to define it, we write that if we have some vectors, let's say we have v1, v2 and v3, and we wanted to take the vector product of that and w1, w2, w3, then this is equal to, okay, so we want to ignore this first column, no, this first row at first, and then cross multiply here. So we get v2 w3 and then subtract this other part, so we have minus v3 w2, and then we carry on doing the same thing. So we get rid of this, and now go on to our next example, multiply these and subtract this in a cross. So we have v3 w1 minus v1 w3, and get rid of this here, and apply the same thing. So we have v1 w2 minus v2 w1, and this is the cross product in 3 dimensions. We also have the cross product in 7 dimensions, but we won't get into that in this video. Okay, so for some properties of the cross product, it might tell you, or rather how the cross product behaves. This might tell you why it could be useful. So firstly we have anti-symmetry, which means that if we have anti-symmetry, which means that if we have some vectors u and vector v, and this is the same as having minus v times u. So as you can see, they're almost commutative, except if you switch them around, we just plop in a negative here. So next, we know it's bilinear, and what this means is that it's linear in both the first factor and it's linear in the second factor. So that if we have some u plus w, for example, or I'll say u plus v for ease, u plus v, and we take the product of that with w, this is equal to u times w plus v times w. And the fact that it's bilinear means that this is also the case in the second factor. So we have that if we have u times v plus w, then this is equal to u times v plus u times w. So what I'm basically saying is that we can expand these out if we want to. And it also means that if we have some constant lambda, some real lambda, and we have lambda u times some w, this is equal to lambda times u times w. And we can do the same thing in the second factor, so we have u times lambda w is again equal to lambda u times w. Okay, and the final property I want to talk about is orthogonality to the input. Orthogonality to the input. Okay, so what this means is pretty self-explanatory. it's orthogonal to the input. So if we recall our consequences of the scalar product video, we know that if we have a dot b equal to 0, then that means that the angle between them is pi over 2, i.e. these are orthogonal to each other, they're perpendicular. So what this means is that if we take some vector v and dot it with v times w, this is going to be equal to 0, because this produces a vector that is orthogonal to both v and to w. Similarly, if we have w dot v times w, this is also equal to 0. Okay. That's all for this video. In the next video, we're going to cover some consequences of the cross product or vector product, or whichever you prefer to use. Thank you for watching. Bye bye.